Happy Friday. 7 weeks down. Insane. Right, so we're coming down to it for our, I don't know, for all of our lessons and everything. We have this, we have like another one or two after that, and that's pretty much going to be it in terms of learning new material. So pretty exciting stuff. And again, so after today, or after this lesson, you would have all the information that you need to pass the matrices PFA. So yeah, you can be able to do that as well. All right, let's kick this off. So we're talking today about two big things, but the first is called the determinant of a matrix. Right? It's a very important characteristic that a matrix has. So the notation that we'll use is either we'll say DET, right, determinant of A, or we'll write it like this, where it's like it's almost like the absolute value symbols. But if they're around a matrix, then it means the determinant. So either one of these is fine, either way. I'll use both. Important thing about a matrix is it can only be found for a square matrix. Okay, so square matrix where the rows and columns are the same. So if any of you attempt to go take the AFA, which will be a little bit more stuff than just the PFA, the AFA asks a lot of like property questions. So one thing that you would have to keep in mind is that determinant can only be found for a square matrix. All right, but if we had like a 3x4 matrix or something like that that's not square, then we can't find determinant for that. All right, so you can only do it for like 2x2, 3x3, 4x4, 5x5, etc. 1x1, I guess. Okay, singular matrix. So if the determinant is 0, then we call that matrix singular. Right, now that's only if its determinant is 0. Okay, so if a matrix is singular, what does that mean? Well, an important part about that is that it has no inverse. Okay, so having no inverse, determinant being 0, and being singular, these are all like the same thing. Right? Because if the determinant is 0, that means it's singular. If it's singular, that means it has no inverse. So all three of these are they're different ways of saying the same thing. Okay, so if I said, hey, here's this matrix. By the way, this matrix has no inverse. Well, then you could automatically say, oh, well, if it has no inverse, then I know that it must be that the determinant is 0. Okay. So we'll talk about what it means to have an inverse or not have an inverse also, but we're starting with just kind of talking about the properties. So these three things are totally equivalent, interchangeable. We're going to stick today with 2x2 determinant. We'll talk about eventually a 3x3 determinant, but determinants are actually pretty hard to calculate once you get into larger sizes. So we're going to stick with 2x2 and 3x3. So if we have a matrix, we'll say A, B, C, D. The determinant, we do A times D. So that would be the product of the main diagonal minus B times C. So that's the product of the other diagonal. Okay. And that's all we have to do to find the determinant. So for 2x2 determinant, very easy to calculate. Okay, just main diagonal minus that other diagonal. Okay, so let's take a look. Find the determinant. Is the matrix singular? Does it have an inverse? All right, so let's start with just finding the determinant. So let's say DET of B, right? Determinant of B is, so we look at the main diagonal, 3 times 5 minus the product of the other diagonal, 6 times negative 2. So So that would be 15 minus negative 12, so 15 plus 12. So the determinant is 27. Great. So is the matrix singular? No, it's not singular. Remember, singular is only if the determinant is 0. So this is not singular. Does it have an inverse? Yes, it has an inverse. Okay. If we say if it is singular, then it means it does not have an inverse. But if it is not singular, that means that this matrix does have an inverse. Okay, and that's all based off of determining whether this determinant is 0 or not. But since it's not 0, then that means that the matrix is not singular, which means that it does have an inverse. All right, let's try that again. Find the determinant. Is it singular? Does it have an inverse? All right, so let's do determinant. Again, this is the other notation. We can either say DET or have like these almost absolute value looking bars. Product of the main diagonal, so negative 2 times 15 minus 6 times negative 5. So negative 30 plus 30, which equals 0. All right, if the determinant equals 0, then yes, this matrix is singular. That's how we tell. If the matrix is 0, that means it is singular. And if it is singular, this means that it does not have an inverse. I guess G. The matrix G does not have an inverse. And we can tell that because the determinant equals 0. So determinant, pretty easy to calculate for 2 by 2. When we go do 3 by 3, it gets more complicated, but not horrific. And then if we go anything above 3 by 3, it gets pretty horrific. We won't do that though, so we'll stop after 3 by 3. All right, one last determinant question, so a little bit different. Given the determinant, find the missing entry. So I start off by knowing the determinant is 30. I'm trying to figure out what value should go here in order to get 30 as the determinant. Well, I already know the formula for determinant, which is the main diagonal, 7 times x, minus the product of the other diagonal, so negative 3 times 5 is negative 15, so minus negative 15 would turn into plus 15. And my goal is that I want this to equal 30, so I'll set it equal to 30. Subtract 15 from both sides, divide by 7. So it must be that that spot of the matrix is 15/7 in order for this determinant to be 30. So just kind of working backwards, but still using our same formula for determinant. Not too bad. So again, as long as you can remember this formula, right, to find the determinant of 2 by 2, A times D minus B times C. Okay, so now let's talk about the multiplicative inverse matrix. So we just call it the inverse. Technically it's the multiplicative inverse to be precise, but we just call it the inverse. And what this is this is a matrix that when you do matrix multiplication, you get the identity matrix as your product. Right? The notation we'll use, just like we use like F and F inverse for functions, So pretty much same thing as we use, if we call a matrix A, then we say this A to the, like almost to the power of -1, right? Or that's what it looks like, is A inverse, or the inverse of A. Okay, and so what it means to be an inverse is, if I do A times A inverse, I will get the identity matrix. So remember, the identity matrix looks like this. 1's on the main diagonal, 0's everywhere else. Or same thing if we do A inverse times A. Either way, I still end up at the identity matrix. It's kind of the same idea like as 7. The multiplicative inverse of 7 is 1/7, because 7 times 1/7 is 1. Or the multiplicative inverse of -12 is -1/12, because that's what you need to multiply it by to equal 1. So remember, the identity matrix is like the matrix version of the number 1. So A times A inverse equals the identity matrix, or A inverse times A equals the identity matrix. Either way. Now, to find inverses can be a difficult process, but for 2x2 matrices, it's actually pretty easy. So the inverse of a 2x2 matrix is this blue formula down here. So if we start with the matrix A, first we take 1 divided by the determinant. All right, that's scalar multiplication out in front of the matrix. And then look what happens. So A D. Okay, those just switch places. All right, but then, so A and D switch places, but B and C, those stay where they are. Look, B is up here, B is still up here, C bottom left, C is still bottom left. The only difference is we multiply B and C by a negative value. Okay, so A and D switch places. B and C stay where they are, but we multiply them both by a negative. And then in front of the matrix, we do 1 divided by the determinant, because the determinant is just some number. So 1 divided by some number, whatever it is. Okay, so let's practice this. Find the inverse and check to make sure it is correct. So I have the matrix 1, 2, 3, 4. Riveting. How exciting. And I want to find the inverse. So the first thing that I need to do to find the inverse is find the determinant. So let's first do the determinant of S. So multiply the main diagonal. 1 times 4 is 4. Minus the product of the other diagonal, 2 times 3, so 4 minus 6 is -2. Oh, keep yawning. Okay, so now S inverse is 1 divided by the determinant. So the determinant is -2. So 1 divided by -2. And then for the actual matrix, so A and D are going to switch places. So 4 and 1. 2 and 3 will stay where they are, but we just multiply them by negative. So that becomes -2 and -3. And lastly, let's just do matrix scalar multiplication. So -1/2 times 4 is -2. -1/2 times -2 is 1. -1/2 times -3 is +3/2. negative 1/2 times 1 is negative 1/2. All right, so let me show you what this means. Let me do the check. 1, 2, 3, 4 times negative 2, 1, 3/2, negative 1/2. All right, matrix multiplication, remember, deals with the rows of the first column, or sorry, rows of the first matrix times columns of the second matrix. So 1 times negative 2 is negative 2. 2 times 3/2 is 3. Negative 2 plus 3 gives me 1. All right, and then we do, come on. First row with the second column, 1 times 1 is 1. 2 times negative 1/2 is negative 1, so 1 plus negative 1 is 0. Right. And then start over, but with the next row. 3 times negative 2 is negative 6. 4 times 3/2 is positive 6, so negative 6 plus positive 6 is 0. 3 times 1 is 3. 4 times negative 2 is negative 2. 3 plus negative 2 is 1. So hey, check it out. 1, 0, 0, 1. That is the identity matrix. Exactly what I said we would get. Right? That's what it means to be an inverse, is when you multiply it, you get the identity matrix. Thank you, Matthew. All right, and it would be the same thing if we did it the other way. Right? If we switched or if we took these matrices and switched places so that this matrix was first and this matrix was second, we would still get the identity matrix. But this only works, remember, we can only find an inverse, so we're only able to find this because the determinant that we got is not 0. It kind of makes sense, too, why a determinant of 0 would mean that there's no inverse. Remember, we have to divide by the determinant here. So if my determinant was 0, and I tried to do 1 divided by 0 times, this matrix, well, I can't divide by 0. It's impossible. So that's kind of one hint or way you can remember determinant of 0 means there's no inverse, because we would end up dividing by 0, which is impossible to do. Okay, let's try another one. Find the inverse. So here's A. Let's first find out the determinant. 10 times 3 is 130. Minus 11 times 7 is 77. So that's 53. Yes. Again, note, the determinant that we got is not 0. So that means that this matrix is not singular, which means that when it says find the inverse, we can do that, because this determinant's not 0. So now we use our formula. The formula is 1 divided by the determinant, so 1 divided by 53. Swap places, so 13, 10 for these two. But for these two, we leave them where they are. We just multiply by a negative. So negative 7 and negative 11. All right, there's two separate rules. That main diagonal, we just switch places. But on the other diagonal, we leave them where they are. It's just multiply by a negative. All right, kind of tough to remember, or tricky to remember. And now let's just do matrix multiplication, matrix scalar multiplication. We have this scalar out in front, 1 over 53. So we'll just multiply everything inside the matrix by 53, or 1 over 53. So 13 over 53, negative 11 over 53, negative 7 over 53, and 10 over 53. Whoa. Come back. I can't write. Here we go. There's my inverse. If we wanted to check if we did A times A inverse, or if we did A inverse times A, either way, we would end up with the identity matrix. Okay, which would prove that yes, A and A inverse are actually inverses. All right, so if you're ever worried, like, wait, did I do this inverse correctly? Well, you could just multiply the two matrices together and try to see, hey, did I get the identity matrix? If I did, then okay, I found the inverse correctly. If I didn't, then something went wrong somewhere. Maybe I messed up my determinant. Maybe I messed up a negative sign or something. Maybe I didn't simplify. Who knows? Yeah. So that's it for 2x2 determinant and 2x2 inverse. I told you it wasn't so bad. Now for 2x2 it's not so bad. 3x3 gets a little worse. But not horrific. 4x4 gets really bad. 4x4 gets horrific. But we won't do 4x4. So that's that last objective for the AFA, or for the PFA. So you now, assuming that you're feeling good about everything that we've talked about with matrices, then you would be good to take the PFA matrices. Yeah, so Aiden, here's the formula for determinant. I'm gonna take it. Yep. And then Aiden, let me know when you're good, and I'll show you the next formula. And then this blue thing, this is the formula for inverse. One divided by the determinant times the matrix, where you switch the A and D spots, and the B and C spots you leave where they are, but you just multiply them by negative. Sure thing, man. Good luck. Okay. Good luck to everybody taking the PFA. That's all for today. Keep it pretty short. We'll come back on Monday, Tuesday. We'll learn some new stuff. Maybe Wednesday, depending on how time goes. And then that'll be the last thing we learn. So exciting. Maddie, good luck. All right, so I will see you guys then. Have a great weekend. Hopefully it's somewhat nice outside. You can head out, do some stuff. But